All right, guys, so this is 4.6. It's optimization problems. We're going to optimize something. That means to find the minimum or maximum value for something. So I'm just going to go through the process once and a bunch of examples, because it's really, that's all it is examples, how to do things. It's just one section. This might end up being a little long because the problems are in fact long. So here's some guidelines. So we're always going to try and identify what's known and what's unknown. This often will involve sketching a picture. We will usually have some sort of what we call a primary equation. In other words, an equation that we are trying to either maximize or minimize. We can often find what's called a secondary equation, which is some other equation that relates to the variables that we're using. And what we're going to do is we're going to use the secondary equation to get rid of what's probably going to be two variables or more in the primary equation. So the primary equation may have x and y and z or whatever. We're going to use the other equation, the secondary equation, to solve for one of those other variables. It's like the substitution method when you were back in Algebra 2, or Algebra 1 maybe. All right? So we're going to eliminate one of the variables using the secondary equation, and then we'll have an equation that just is one variable, which we can maximize by taking its derivative, setting it equal to 0. We can either do a candidate test from there to figure out if it's an absolute max or an absolute min, or we can do a second derivative test to figure out if it's a relative min or a relative max. And always keep an eye on your domain, so you make sure your answers are in your domain. All right, since these are often real-world application problems, they will often have what we call ugly answers, like long decimal answers. They won't necessarily be whole number answers. So you will likely need your calculator to solve some of these problems. All right, so that being said, here is an example. A cardboard box maker wants to create a box with a square base, a surface area of 108 square inches, and a maximum volume. What dimensions will produce a maximum volume? So they're making a box. The box has to have a square base. The height we can change. So the box could be really tall or the box could be really short. But we want it to have a maximum volume. All right, so in other words, here's our box. We can say the bottom is x by x and the height is h. So now we're identifying knowns and unknowns. So we don't know any of those sides. We know that the volume is what we want to maximize. And that would be x times x, so x squared, times h. All right, that's our primary equation. That's what we want to maximize. Secondary equation. So the other thing they tell us is this thing about surface area. All right, well, surface area for a cardboard box, which I guess we'll assume has an open top. Looks like it's open to me. So we'll have a bottom area of x squared. And then all of these sides are x by h. The height is h for each one of them. So we have one side here, one side here, one side in the back, one side over here. So there'd be 4 of them. So there's 4 x times h sides. Now if we had a top here, which maybe we do, maybe we don't, we would just add another x squared. So there'd be 2 x squareds. But that is our surface area. And we were given that that is 108. So that's our secondary equation. So that's the equation that relates the variables together using other information we've got. Now we want to eliminate a variable in the primary equation. So we want to get rid of one of these variables. We can probably solve for h here and then plug that answer in there. So the way that we would do that is we would subtract x squared from both sides and then divide both sides by x. Now we've solved for h. So now we take this guy and we're going to plug it in for h. So we get that our volume equals x squared times 108 minus x squared over x. We can simplify this a little bit. One of these x's is going to cancel out that x down there, and we can distribute. We get that our volume is 108x minus x times x squared is x to the third. So now we have an equation that we want to find the maximum of with just one variable. So now we're on step 5. Take its derivative, set it equal to 0. So the derivative here is going to be 108 minus 3x squared is equal to 0. All right, notice I didn't put a times dx dt and I didn't put dv dt over here either, because these sides aren't changing. It's not like we're moving this box around. Like, this is going to be some fixed x. This is also fixed. They're not moving. So that's how optimization problems are different from related rates. Related rates, everything is moving or can change. this is going to be some fixed answer. So now we just want to solve this. I just move the 3x squared over, divide both sides by 3. Let's see, 36 equals x squared. Take the square root. Technically, we're going to get x equals plus or minus 6. And now here's where we're mindful of our domain. Does it make sense to have a negative length? Probably not. All right, so it looks like x equals 6 would be the only thing in our domain. Okay, so now we need to check to make sure that this is going to be a maximum and not like a minimum. So one way we could check is we could take the second derivative. So this was v prime. So we could find v double prime. It'd be negative 6x. If we just take the derivative of this, derivative of 1 away to 0, derivative of negative 3x squared is negative 6x. If we plug in 6, we're going to get negative 36. That means we are concave down. That means we are going to have a relative max. So this is indeed a maximum. So x is 6 as part of our answer. All right, our other answer is going to be, what's h? Well, we can plug it back in. We get h equals 108 minus 6 squared divided by 6. So 108 minus 36 divided by 6. I don't know that off the top of my head. It's probably a nice number. In fact, I think it's going to be... Where's my calculator? 72 divided by 6 gives us 12. That looks right. So it looks like the height here is going to be 12. Now remember, we're working in inches, so don't forget to put in units. Inches. Oh, done. Ta-da. All right. That's how we optimize. Next one. Find two numbers that sum to make 20 and multiply to make a maximum. All right, so identify our knowns and unknowns. We'll call these numbers x and y. Two numbers. We're just using variables. Primary equation. They want to multiply to make a maximum. So x times y is equal to a maximum. Secondary equation. Well, we're also told that they are going to sum to be 20. Eliminate a variable. Well, let's solve for y. All right, so now we can take this 20 minus x and we can plug it in up here for y. So we want to maximize this expression, x times 20 minus x. All right, so now we have a choice. We can take the derivative like this, or we can distribute and then take the derivative. I think it's probably going to be easier if we distribute first. And now we're going to take the derivative. So we'll get 20 minus 2x. We want to know when that equals 0. So we're going to get 20 equals 2x, divide both sides by 2, x equals 10. All right, now we can plug back in right here, and we will get y equals 20 minus 10, also 10. So our answers are 10 and 10. That one was pretty quick, right? All right, the only domain issue is x needed to be less than 20. That's not a problem. It needed to be greater than 0. Also not a problem. And I believe that's going to maximize. And the way we can check that it is a maximum would be the second derivative here. So the second derivative would just be negative 2. I was calling that max, so it would be max double prime. So we're concave down, and it is a maximum. All right, let's get a little tougher. Which points on the graph of y equals 4 minus x squared are closest to the point 0, 2? Well, let's draw a graph. Yeah, I'll do a graph. I know, I cheated. I'm sorry. So here's the parabola 4 minus x squared. We're going to have some point, probably points because it's a symmetric graph. xy is a point, and we want to be the closest to 0, 2. So we want this distance to be a minimum. So we want to minimize d, which is equal to, now we need to do the distance between these 2 points. We'll just use the distance formula. The distance between 2 points is the square root of x minus this x value, so x minus 0 squared, plus y minus this y value, y minus 2 squared. All right, so there's our formula to minimize. Next, we need a secondary equation. There it is right there. That relates x and y. So I can now plug in right here and say, okay, well, distance equals the square root of x minus 0 squared, and I guess we can still write minus 0 if we want, plus, and now instead of writing y, I'm going to write 4 minus x squared minus 2 squared. I have plugged in this function here for y right there. All right, now I want to simplify a little bit. All right, before I try and eliminate, so I've eliminated a variable. Before I want to try and minimize, I want to simplify. So we're going to have the square root of x squared plus 4 minus 2 will be 2 minus x squared squared. All right, so now we have some options. We can try and take the derivative of this. We can try and simplify what's in here a little bit more. That might be the thing to do. We can also square both sides. All right, so when the square root of something is minimum, the inside needs to be a minimum. So we can just kind of forget about the square root and say we want to minimize, just to make our lives easier, or we can square both sides and say we want to minimize d squared. We want to minimize d squared, which is equal to x squared plus 2 minus x squared squared. All right, and minimizing this will get us the same answer as minimizing this square root function up here. All right, so now we can take the derivative. So the first derivative equals 2x plus, we can do a chain rule here, 2 times 2 minus x squared to the first, times rid of the inside. All right, and we want to set this equal to 0. We're probably going to want to simplify this. So we get 2x plus distribute, we're going to distribute a negative 4x times 2 is negative 8x. Negative 4x times negative x squared is positive 4x to the third equal to 0. All right, we can factor out an x from everybody, and we can actually put these two together first, actually. We'll get 4x to the third minus 6x. Factor out an x. Actually, factor out 2x. We'll be left with 2x squared minus 3 equals 0. So from this guy, we're going to get x equals 0. Interesting. That's probably going to be the max for this little section here. From between here and here, that's going to be the farthest point away. But we'll check on that later. From this guy, we're going to get x squared equals 3 over 2. So x equals plus or minus the square root of 3 over 2. All right. Now let's see which ones of these numbers are mins and maxes. So here's our derivative right here. This was simplified. Let's look at our second derivative. Will then be equal to, that'll be 12x squared minus 6. All right, if we plug in 0, that's going to be, so at 0, we get negative 6, which means we'll be a max, and we were trying to find the closest. We're trying to minimize, so that's not our guy. At x equals the square root of 3 over 2, we'll have 12 times square root of 3 over 2 squared, so 12 times 3 halves minus 6. So that's 6 times 3 is 18, minus 6 is positive 12. That means we are concave up. That will be a minimum. The same thing will be true for the negative. So that means these guys are our winners for our x values. If we need to find our y values for the actual point, we would plug back in to the original. So y equals 4 minus the square root of 3 over the square root of 2 squared. Don't know why I decided to split it up there, but y is going to equal 4 minus 3 halves, or 8 halves minus 3 halves is 5 halves. So we get the points root 3 over 2, 5 halves, and negative root 3 over 2, 5 halves. There's our 2 points. Those two should minimize that distance. All right, the classic book publisher problem. So a rectangular page is to contain 24 square inches of print. So that's this section in here, 24 square inches in here of print. The margins at the top and bottom of the page need to be 1.5 inches. So top and bottom, we've got 1.5 inches right here. Same thing on the bottom here, 1.5 inches. If you look at a book anywhere, there is usually some room at the top and bottom of the page. And the margins on the left and the right are to be 1 inch. So we had 1.5 there. So on the sides here, we've got 1 inch. Yep, there's our 1 inch right there. Same with over here, we've got 1 inch. All right, what should the dimensions of the page be so that the least amount of paper is used? So we're going for the least. So that means we are trying to minimize the area. In the area here, let's see, if we said, there's two different ways we can do this. We can say the whole thing is x by y, and then we'd have to subtract these little margins, or we can say the print part is x by y, and we can add in the little margins. But don't forget in the end, what we're looking for, the dimensions of the page. So with the picture that's drawn here, we're going to have to add in 2 for the y, and we're going to have to add in 1.5 and 1.5, so 3 for the x. All right, but the area of the page, no, I don't want to, area will be equal to, let's see, this side is y plus 2, this side is x plus 3. So there's our function that we want to maximize. That is our primary equation. Our secondary equation, all right, we're told we want 24 square inches of print. So that means this little section, x times y, is 24. So there's our secondary equation. I usually like to solve for y because I like to take derivatives with x's. 24 over x. And now we can plug that in right there. So we get that the function for our area is 24 over x plus 2 times x plus 3. It's probably going to be easier if we distribute here or FOIL this out before we do our derivative. So x times 24 over x is just 24. Outer, we get 3 times 24 is 72 over x. I think that's right. Then we get a 2x, and 2 times 3 is 6. So we're getting 30 plus 2x plus 72x to the negative 1. All right, the reason I wrote it that way is because that's going to be the easiest way to take the derivative. So the area prime is going to be, derivative of 30 is 0, derivative of 2x is 2, derivative of that is negative 72x to the negative 2. We set that equal to 0, and now we are solving. So we're going to get, we can bring this back down, we get 2 equals 72 over x squared. Multiply this up over here, 2x squared equals 72, divide by 2, take the square root, plus or minus 6. Now here's where our domain comes in. Negative 6 does not make sense. All right, we got a length. So it looks like x equals 6. We could probably check our second derivative just to make sure. Area double prime is, the derivative of 2 is 0. Bring down a negative 2 here, we get 144 x to the negative 3. If we plug in 6 there, it's going to be positive, which means we are concave up, which means we are a relative minimum, and we were trying to minimize, so that works. So it looks like x is going to be 6, and that tells us that y is 24 over 6, which is 4. But don't forget, we want the full margins of the page, so the page is going to be 6 plus 3. 6 plus 3 right here is 9 inches by, all right, 4 plus 2 is 6 inches. So those are the dimensions of our page. All right, I think this is the last one, and this is probably the trickiest one too. All right, so 4 feet of wire. So we have 4 feet of wire is to be used to make a square and a circle. All right, so we're going to probably cut the wire somewhere, and some of it's going to be folded together to make a square. Some of it's going to be rounded up to make a circle. How much of the wire should be used for the square, and how much of the wire should be used for the circle if the area of the enclosed by both figures is to be maximum? All right, so we want the area to be a max, and we're going to have a circle and a square. So side squared for the square, pi r squared for the circle. Who knows what we're going to use there, but just writing it down for our primary equation right now. So we've got 4 feet, and we're going to cut it at some point. And we're going to make a square out of this, so we'll call maybe this L, and then this would be 4 minus L, right? The length for L. And this one's going to be our square, and this one's going to be our circle. All right, so now our square, we're going to take this and bend it around to make a square. Each of these sides is going to be L over 4. So x in this function up here is going to be L over 4. All right, over here, the circle, we're going to take this and we're going to make it into a round circle. So that means the circumference here is 4 minus L. Circumference is 2 pi r. So that means our radius, for this radius here, is if we just divide this. So r will be 4 minus L over 2 pi. So now we've got pi involved. Chances are we're not going to have a nice answer. But now both of these have functions in terms of another variable L. So we've got our secondary equation. We're going to plug those in. We're going to get our area is L over 4 squared plus pi times 4 minus L over 2 pi squared. So now we have eliminated both variables and plugged in this new variable L, which is actually what we want, the length that will yield the minimum area. All right, so now we want to maximize or minimize this. So let's try and simplify it first. So L squared over 16 plus pi. Let's see, do I want to distribute that or not? We'll just leave it as 4 minus L squared over 4 pi squared. We can square the bottom though, and that's going to cancel out one of those pi's. All right, now we'll go ahead and take the derivative. So this is area in terms of L. So a prime of L would be, bring down the 2 L over 16 plus, bring down the 2 here, we're doing a chain rule, 2, 4 minus L to the first times root of the inside, which is negative 1, over 4 pi. Bottom doesn't change, it's just a constant. And now we want this to be equal to 0. So let's see, we get L over 8 plus the 2 and the 4 will cancel. We'll get actually minus. I have an eraser somewhere. Ta-da, there's my eraser. Minus 4 minus L over 2 pi equals 0. Let's go ahead and add this over maybe. L over 8 equals 4 minus L over 2 pi. Cross multiply. 2 pi L equals 32 minus 8L. We will add this guy over. 2 pi L plus 8L. So 2 pi plus 8 times L equals 32. And then divide. Ta-da. We can cancel out a 2 here from everything. It'd be 16 over pi plus 4. Now, we do need to check and see if this is a minimum or a maximum. So we want to take another derivative, and let's start with, let's see if I can write this somewhere nicely. So we had L over 8 was our first derivative, minus, we'll just go ahead and distribute this, minus 4 over 2 pi plus L over 2 pi. I'm not even going to try and simplify this because when I take its derivative, it's going to cancel. So the second derivative here is 1/8 minus, actually nope, that's going to go away, plus 1 over 2 pi, which is positive, which means we're concave up, which means that this is a minimum. Uh-oh. Now what? So the one thing we found gave us a minimum area. We wanted to know what was the maximum. How do we find the maximum? All right, now the domain comes into play. So our domain was probably from 0 to 4. Remember, we've got the length of this, it's 4 long. So we can either cut it at 0 and say the whole thing is the circle, or we can cut it at 4 and the whole thing is the square. So now we're doing our candidate test basically. We know that this guy's a minimum, so we don't have to try that anymore. But we need to try 0 and 4 in this, our area function, or in this if we want. Either one of them is fine. All right, so if we try 0 here, the area when L is 0, so this is 0, so we get 0 squared. This is going to be 0, so we're going to get 4 squared over, and we had 4 pi on the bottom. So that's 16, actually, no, sorry. That's going to be 4 over pi. Where's my eraser? All right, so we got an actual answer there. What if L is 4? Well, if it's 4, we get 1 squared, and this other guy is going to be 0. So we get 1. So now, which is bigger? 4 over pi or 1? All right, 4 is bigger than pi. So 4 over pi maximizes our area. In other words, we are going to have 0. L is 0. So that means we have 4 feet of circle. No square. That is how we're going to maximize the area. The circle's area is always going to be bigger than a square's area if we have the same circumference or same amount of perimeter. All right, so that's going to be our answer. This was a sneaky one, so don't forget to check your domain, and don't forget to do your second derivative test to check to see if it's a min or a max at the end. All right, and this would probably be our minimum, going to give us our minimum area, but I'm not going to try and plug that in up here. All right, so that's optimization problems. As you see towards the end there, they can get pretty tricky, but they can also be pretty straightforward. So just, they start easy and they get harder. So good luck. We'll go over some in class, I'm sure.